Okay, so we want to transition now to talking more about particle motion. And I want to take a look again at our course objectives. So our first objective was to characterize aerosol particles using different kinds of size distributions in basic aerosol chemistry. And so we've done a lot of this in the first couple of weeks of the semester. We've talked just now about very basic aerosol chemistry, but this is mostly to come. In the second part of the class, we'll talk more about aerosol chemistry in a more rigorous manner. So where we're headed now is the second objective. We want to predict how an aerosol particle can move through a fluid with and without external forces. And so in order to do that, we're going to need to talk about the gas phase using our particle kind of size spectrum. We need to understand what's going on over here at the very smallest sizes. These are gas molecules, smaller than even nucleation mode aerosol. And the reason we need to understand gases is because the aerosol particles are suspended within the gas phase, right? And so the way that they move will depend on what is going on in that gas phase. So I want you to take a minute or so and just think about what information we might need to know in order to predict how aerosol particles are moving within the gas phase. So hopefully you've had a chance to think about that. If not, you can pause and think more. But we can kind of use the analogy of a billiard table or a pool table. That will work fairly well for us. And we can think about the gas molecules as billiard balls and say, we place something on the billiard table, say like a tennis ball, which is our aerosol particle. And it's going to be pushed around then by the billiard balls on the table. And so one thing that we will need to know, right, is how fast our gas molecules or our billiard balls are moving, right? When things collide, then there is an exchange of momentum, and more momentum will be exchanged if things are moving more quickly. We need to know how fast the molecules are moving. We also need to know kind of how many billiard balls are on the table. How far can they travel before they collide is another way of saying that. How much empty space is there is maybe another way of thinking of it. If there is kind of more empty space or the molecules can travel further before they collide, then that will mean that the aerosol particles suspended in the gas phase will move in a different way than if the molecules are closer together, more crowded, they travel less far before colliding. And a third thing that we need to know then is how efficiently the molecules are transferring momentum. If that is more or less efficient, that affects then, right, how fast the aerosol particle, which is being collided with, will move. And so conceptually, these are kind of the three questions that we want to get a handle on with regard to gases. How fast are the molecules moving? How far do the molecules travel before they collide with one another or with the aerosol particle? How effectively do the molecules transfer momentum amongst each other and also with respect to the aerosol particle? And so to answer those questions, then we need to make a few assumptions about how the gas phase works. And we encapsulate these assumptions in what we call a kinetic theory of gases. And so I think most people should have heard of the kinetic theory of gases. You see a GIF here from Wikipedia that is kind of that billiard ball analogy that I was just talking about. And the billiard ball analogy is basically the core of the kinetic theory of gases, that the gas molecules behave much like billiard balls on a billiard table. So more precisely, that means that molecules are small relative to the distance between them. There's a lot of empty space in this kind of box here, and the billiard balls are just kind of knocking around within the box. A second assumption is that the molecules are just moving randomly. They have a fixed distribution of speeds and they undergo frequent and elastic collision. Elastic collision is important. It means when I collide with something else, there is no loss of momentum to something like friction. So all of my momentum is exchanged to the molecule with which I collide. And the last assumption is that there are no external forces acting upon the gases. There's no gravitation, attraction, or repulsion between the molecules. And that sort of feeds into the second assumption that allows the molecules then to move randomly with this fixed distribution of speeds. So these are our three assumptions of the kinetic theory of gases. And then we want to talk about this distribution of speeds. All right, this is our first question. How fast are the molecules moving? The distribution of speeds of molecules can be described by the Maxwell-Boltzmann distribution. So we've been talking about distributions, but of aerosol size. This is now a distribution of molecular speeds. I'm going to call speeds C. So F of C means what fraction of particles have a velocity C. And you can look at this functional form then, and C appears in the prefactor, but also in a second exponential decay factor. And so what that means is that the Maxwell-Boltzmann distribution will be non-monotonic. It'll have a portion where the fraction of particles with the velocity C increases, and then a portion where the fraction of particles with a velocity C decreases. Then we want to define the other variables that are in this Maxwell-Boltzmann distribution. M is a mass of molecules. What is my molecular mass? K sub B, or just K here, is a constant. It is the Boltzmann constant, equal to 1.38 times 10 to the minus 23 joules per Kelvin. And T is then a temperature that characterizes the gas. So this image from Wikimedia shows a few instances of the Maxwell-Boltzmann distribution. First in blue is for a temperature of 100 Kelvin, which is quite cold. When the gas is so cold, then the molecules will move more slowly. And also the distribution will have less spread. So things will be somewhat less chaotic. That's kind of what we expect intuitively, right? If a fluid is colder, the molecules within it move slower and also less chaotically with less spread. That is in contrast then to this distribution over here at a temperature of about 3000 Kelvin, which is not quite the surface of temperature of the surface of the sun, but getting close to the temperature of the surface of the sun. And there, right, the center of the Maxwell-Boltzmann distribution is at a much faster molecular speed, and there is also a lot more spread. So the molecules are moving much more quickly and also much more chaotically. And I should point out the magnitude of this speed, right? Something like 1800 meters per second. That is faster than Mach 5, right? Faster than the very fastest jets that we have in the atmosphere. And so these molecules, especially at high temperatures, are really moving very, very fast. So we talked about a number-weighted diameter for aerosol sizes. We can, in the same way, calculate the mean speed of our molecule, C bar, by taking the molecular speeds and weighting them by this distribution of speeds, right? And then integrating over all the possible speeds from 0 to infinity. And if we do that for this functional form of the Maxwell-Boltzmann distribution up here, then we get a mean molecular speed, which is 8 times the Boltzmann constant times temperature, over pi times the molecular mass all to the 1/2. That is our mean gas molecular speed. And so then we've mostly answered this first question. I'm going to switch to paper in just a minute to show this idea of a root mean square speed. But we've defined a mean speed, C bar, and then we've defined this Maxwell-Boltzmann distribution. And we've said as the gas gets warmer, we shift towards faster speeds and a greater spread in those speeds. It's important then to say also, if we move towards lighter gas molecules, right? So from something like oxygen that you see in red here to something like hydrogen, which you see in orange, then the same is true as increasing temperature. So if we have a less massive gas molecule, then it will move faster and it will also move more chaotically. Again, that should be fairly intuitive. If we increase temperature, we increase the mean speed or the root mean square speed with which the molecules move, and we increase the spread in our distribution. For molecular mass, it acts the opposite way. If we increase the molecular mass, we decrease the mean or root mean square speed of the molecules, we decrease the spread in the distribution. So I'm going to pause here and do some work on paper, both about the root mean square speed, but also how far the molecules are traveling before colliding with one another.